Welcome to the course on Introduction to Global Health Research, but also health research in general. We will cover a number of topics, starting today with just basic epidemiology, statistics, and evidence, which is usually in the root of every health research. My name is Igor Rudan. I'm a professor at the University of Edinburgh, professor of international health and molecular medicine, and I co-lead the Center for Global Health Research here and the World Health Organization Collaborating Center. So this lecture, the first in the series of 7 lectures, which is going to span across the fundamentals really of health research, is going to be covering the topics such as what is the definition of epidemiology? Can we think about where the epidemiology came from and where it developed from? What are the uses of epidemiology these days? What is the epidemiological method? What study designs can we use in health research? A little bit about statistics and evidence, and showing that statistics is really just serving the research, but it is the design that is everything. Statistics then just helps at the end, but conducting the research is really much, much more than statistics. Many people think when they start getting into health research that this is all going to be statistics. Many people are just scared and worried that this is going to be about numbers and mathematics and complicated formulas. In fact, I will try to convince you through this course that it's all about very good design of the study and planning your study and thinking through all the possible biases and confounding and chance effects. And if you plan your study well and design your study well, you hardly ever even need the statistics. That's just something that you do at the end to please the reviewers and to publish the paper. But if you've done your work well, then statistics doesn't come into play at all. It's almost unnecessary. Whereas if you didn't think through your study design, and if you didn't think about what you're doing and didn't plan the study well, if you made a lot of mistakes conducting the study, then no statistics can possibly help your research and your work. Finally, there's going to be a little bit about how we assess this course. Okay, moving on. So what is the definition of epidemiology? This word comes from roots epi, demos, and logos. You know, in ancient Greek, this was about the people of districts, a study of. What does this mean? Well, doesn't look like it means anything much, right? But this is, I like to think about it as something that came about the people. So if you think of the population, then these are some problems that are burdening this population, that came on the top of them and that are concerning them in some way, right? And you can see here your population, and then these people here suffer from first disease, these people here from the second, third, fourth, and so on. And you can even see that some diseases are overlapping and some people are suffering from more than one disease, right? So we can think of epidemiology as a study of the distribution and the determinants of disease in some population of our interest. So when we do our studies well, then we end up with something like this map here. We can see very clearly that these are the causes of child deaths in the world, so we can see very clearly which regions of the world are we talking about, and what is the distribution of these deaths. You can see that most of them are happening in Africa and Southeast Asia. Just many more, far fewer we can see in these developed regions of the world. And not just that, because the size of a pie tells us the size of the problem, but also you can see that various colors are telling us about specifically what causes underlie this research. So this is what we're interested in. If you remember, that came about the people interpretation, then you can think of it as these big circles coming over the population, and the size is showing you what is the size of the problem, and then you want to know also the distribution. And when you have information like this, then you can start doing something about the problem. So the first step in health research is always define the problem and define the size of the problem, and then you can start exploring why this problem happens and what can you actually do about the problem. So it is not only the burden which is shown here, but it's also the architecture of this burden that we're interested in, and also the interventions that we can apply in order to get rid of this burden. And this is going to become a running theme throughout this whole course. You know, I'm always going to be getting back to this, that in epidemiology we are interested in defining the size of the problem first, and even before that, defining what the problem is. What do we mean by the problem? So we need to define the problem, then measure the size of the problem, and then try to understand the causes of the problem. Those are the risk factors, and also trying to understand the solutions to the problems. Those are the interventions. And you will see how it's all interconnected in each population and how it tells you what to do. So this is the job of a researcher in global health, to try to define a problem, explore the size of a problem, define the risk factors that contribute to the problem, and then explore the effectiveness of interventions to remove this problem. That's a lot of research in global health falls under those categories of epidemiological research. We have some other categories of global health research, such as health policy and systems research is a very, very useful type of research. Or you can focus on specific interventions and then do the research how to make those interventions better, more implementable, more acceptable to people. So that's a special kind of research. And then you can do basic research, fundamental research, to try to develop completely new interventions that do not yet exist. So those are some big areas or instruments of health research in global health. But today we're going to be focused on epidemiological research, which is, again, defining the problem, defining the burden of the problem, trying to understand the causes of the problem, and also trying to explore the interventions that can help to remove this problem. So remember distribution and determinants of disease in this definition. So now everything that I was just saying, I will try to visualize for you. So basically you come to a population, and this is what an epidemiologist does. Comes to some population, explores, and what are we interested in? Firstly, if all these people together could complain about every single complaint they have about their health, and if they can all put it in one big barrel, then this would be their joint common burden of disease. So let's say that each and every one of these people tells you all their health problems, and you put it into this barrel, and then they just keep, and this is what it looks like when they do this. So this is the burden of disease that you're encountering in a population. But then the situation is never as simple as this. It gets more complicated because some of these people choose to do something that damages their health. For example, these people here may be drinking. These people here may be smoking, and you can see that some people are actually both smoking and drinking. And then these people here could be living in a household where they use solid fuels and the air quality is bad. And you can see that there are some unfortunate people who are exposed to all of those risk factors at the same time. So because of this exposure to unhealthy behaviors, the burden grows. It's not as simple as just people without any risk factors. Because of these three risk factors, the burden goes up, and it goes to this level. And then you come to this place and you're thinking, oh my goodness, okay, there is this population, there is this burden, and then because of these risk factor exposures, the burden is higher than it should be, really. But at the same time, the situation is never as bad as it can be, because the government usually puts some efforts into preventing disease or treating disease. So let's say that there is an intervention one, which is, say, vaccination. So all these people have been vaccinated. So because of this, the burden is actually smaller than it can be. And also, these people are maybe having some anti-alcoholic support group, so they are free from drinking alcohol, which is good, because otherwise the burden could have been even greater. So thanks to those interventions, the burden actually is decreased somewhat, okay? And then this is what your job is, to come to a population and to define the burden of the problem, and to also understand the architecture of this burden. So why is this burden this big? What constitutes this burden? What kind of combination of baseline risk plus the risk factors plus the interventions all together form this kind of the burden of disease? Because the burden is fluid. You could see that it can go up, it can go down. So the burden is something that constantly changes, like stock market prices. Why? Because in stock market you have optimism, you have pessimism. Here you have risk factors, here you have interventions. So if the risk factors prevail, then the burden goes up. If the interventions come in and prevail, and people avoid risk factors, then the burden goes down. So the burden fluctuates, and you need to, when you capture the burden, you need to understand that this is something just temporary at the moment, and you need to try to understand how does this architecture of the burden causes this burden to exist, and what could we possibly do to remove the risk factors and to add more interventions, and then to get rid of as much of the burden as possible. So this is why epidemiologists are interested in measuring the burden of the problem and risk factors and intervention effectiveness, okay? Now, have we been successful as epidemiologists in the past? What do you think this is? This is, you see year, you see population in millions. So this is the world's population, human population, all right? And look, 40,000 years BC, we only had 2 million people. And in fact, there were like 10 species of humans walking the surface of this planet, and 9 of them are gone. They didn't survive. Why? Because they were always struck by various epidemics. That is the biggest cause of death historically, which wiped out many species. There were 5 billion species on Earth in its history, people estimate, but now we only have about 10 million left. So more than 99% of species are gone, and mainly they are gone because of not being able to deal with infectious diseases. Okay, some of them were eaten, some of them experienced hardships because of cold or climate change or volcanoes or meteors, but in fact the most dangerous thing for human species have been infectious diseases, and this is something that's been causing vast majority of death historically for human population. So at the time of 40,000 BC, there were only 2 million humans on the planet, and we were very vulnerable to some pandemic that could wipe us from the planet. At this time, surely about 9 out of 10 deaths, if not more, have been due to infectious diseases in human population. And the same continued to 10,000 BC, where we had 4 million people, 7,000 BC, and you can see at the year 1, we had already about 170 million people. So that's much better, that's much safer. But look what happened. We didn't really make much progress because many children were born, but many people were also dying, and many children were dying in particular. Probably 1 in 2 children historically were still dying even at this time because of all sorts of infectious diseases. All the diseases that we vaccinate against these days, like smallpox, and then you had pneumonia, diarrhea, malaria, all sorts of childhood diseases, tetanus, pertussis, diphtheria, morbilliparatitis, rubella. So you had a range of diseases, and it was even difficult for any human to survive the first 5 years of life. Most of them would probably die even before, and those who survived would probably not live that much longer because they were living in all sorts of conditions. There were famines, there were hunger and terrible climate and so on, and people would be dying very young. Okay, but look what happened. Somewhere around this time here, there is an explosion of human population. In fact, if you just take the year 1900, which is hardly 100 years ago, and you look at the population of 1.5 billion, and now we're at 7.5 billion, 100 and a few years later. This means that the human population has increased 5 times. There are 5 times more human on the planet now than 110, 20 years ago. That is remarkable. And how did this happen? It happened because of some remarkable individuals who single-handedly doubled the number of humans on Earth. Hippocrates was the first one when he started being interested in hygiene and health issues and thinking about prevention more, not just treating wounds and infections, but he realized that prevention is very important and we need to be in a sanitary condition and how to treat wounds and infections as well. But then Girolamo Fracastoro was a person who was the first one to think that infectious diseases may be due to some invisible microorganism. Can you imagine that for all this period of human history, people were dying, you know, the whole villages would be dying, people would come, and people didn't know why, because no one could think that this could be due to some tiny things that we can't see, because people thought that we can see everything there is to see. I mean, they looked around and they thought they could see everything. They didn't think that there could be something so small that they couldn't see it, and it could be alive and it could be spreading and causing them death. And then you know that Jenner introduced vaccination. It's remarkable that this worked. It used our own immune system to fight this off, and he probably single-handedly saved more human lives than any human in history. And then Alexander Fleming from Scotland here invented, by some luck, antibiotics. And those two have now led us into the only period in history of humans where we are no longer that scared of infectious diseases, which is remarkable because for all human history, infectious diseases were decimating our population. They were causing 9 out of 10 deaths. And now they're causing maybe 2 out of all 10 deaths in the human population, and they're being reduced all the time through vaccination and antibiotics. So what a transition. And look, as a result of this transition and our dealing with infectious diseases, the human population just exploded because people were no longer dying at the age of 20, 25 or 15. Children stopped dying and they all grew to be adults, and suddenly you have this population explosion. So let's remember a little bit what it looks like. So until the 16th century, every epidemic disease was called pestis or pestilentia, which is plague, because people didn't know that this was caused by microorganisms, and they didn't distinguish various microorganisms. They just, anything that was causing massive mortality, they called plague. And Girolamo Fracastoro, whom I mentioned, was the first one to hypothesize that diseases may be spread by very small particles, which he called microorganisms. And in his book in 1543, he hypothesized that these could reproduce, that they can multiply, that they are poisonous, that fire can destroy them, and that sanitation is very important. And all of this is true, but he did this blindly. He just thought of this without being ever able to prove any of this. So he basically died without knowing whether he was right or wrong. And look, in 1670, so about 100 years after Girolamo Fracastoro died, Antony van Leeuwenhoek in Holland developed a microscope, and people could suddenly start seeing things that they can't see with their naked eye. And he proved the existence of microorganisms. It was incredible to be able to take some material from a flesh wound and look at it under the microscope and see these little things there being alive and multiplying and causing trouble. So that was unbelievable. Imagine that kind of discovery suddenly, that there are micro worlds of living particles that you had no idea about, and they could be causing all these problems to humanity. And then some heroes, again, John Graunt in England, he's published his Bills of Mortality. That was the first really attempt to go around, because people were living in small villages in those times, and they were not aware of kind of like wider population problems. So he started going from village to village and collect from church records the causes of death and build a bigger picture of what are people dying of. So this was the first kind of like epidemiological thinking of defining the burden and the causes of the burden. And then you had James Lind here in Scotland, who has conducted the first trial. So British Navy was a big navy. It was dominating and controlling the world in these years, and most of people weren't dying on those ships in battles of any sort, but actually they were dying from scurvy. And he hypothesized that if you eat citrus, you could perhaps prevent this disease or treat it. And he separated people from the same boats in a group that was getting citrus and the group that didn't, and he realized that this really does the trick and prevents the development of disease. So this was a huge finding and very important for Britain at that stage. Edward Jenner, I mentioned, my all-time hero, obviously, he has managed to figure out that you can vaccinate to prevent disease. It was all by working as a GP in one village and noticing that you can provide the cross immunity to smallpox to children in the village if you cross immunize them with cowpox. Then John Snow conducted the first ever community-based trial which proved that cholera in London was caused by polluted drinking water, because people thought that cholera was being spread by bad air, but he took great care to think where all cases are coming from, and he could see that they're all clustering around one pump, and then he hypothesized that water may be to blame, and did various things to prove this. Then Louis Pasteur clearly took everything many steps further. He not only developed many vaccines based on following up on work by Jenner, but the other problems with microbes in those days was that food was poisoned and drinks were poisoned. Milk, beer, anything would get poisoned very soon. And if you didn't know how to keep them under conditions to prevent them from going bad, you would get all these problems, and people were sick and dying from food poisoning and poisoning of whatever they ingested. And finally, you had Alexander Fleming here in Scotland, who discovered penicillin, and this is now keeping us safe from many bacteria these days. Okay, so thinking back to this development of problems and their solutions, obviously, epidemiology was mainly focused on etiology and transmission of infectious diseases, and this is really something that began as a field in 1850. And then it moved to etiology of chronic disease in 1950, then health status of population and planning health services around 1960. Effectiveness of medical care became of interest again in 1960s, and then it moved into clinical setting, and the clinical epidemiology was developed in 1970s, and finally nowadays we even have molecular and genetic epidemiology developing from 1980s. So you can see how logically epidemiology was being developed, and it's still developing. This is not nowhere nearly the final stages. Now, there is something that's called epidemiological method that has really helped us to achieve all this progress and improve health. And what is epidemiological method? Well, this is a process which has these stages which I tried to explain very early in this lecture. Firstly, you define the disease. You have to say what do you consider a disease versus a healthy status. And this is not always simple or easy, and doctors may not always agree that someone does or does not have a disease. So case definition of the disease is the first step. You need to be very clear about case definition so that you can compare various estimates of the burden across many countries or cities or places and populations, right? So the next thing is then counting the frequency of disease in the population. Clearly, you have defined what do you mean by disease, and then you have to go into your population and say how many people in the population have a disease or not. Now, this population doesn't need to mean the whole population of a city. It can mean just a sample. So we're talking about counting the frequency even in a sample of the population. That's fine too, and we will see how we actually use this later. Then, describing the occurrence of the disease in the population. So this is now talking about being more specific rather than just taking some sample or some population and counting the number of cases of disease. This is now talking about cross-tabulating and making first analytical insights and comparisons. This means, let's compare these numbers by age. If older people are having more disease than the younger people, if people of male sex are having more disease than the people of female sex. So suddenly, not only that you have the number of people with disease and number of healthy people, but now you're using those numbers to somehow derive some knowledge from it, okay? So that's the next step. You're cross-tabulating the number of disease against various other factors. And finally, the final stage is comparing the disease occurrence between two different populations. So this is when you want to know whether one country has a bigger incidence or prevalence of some disease than the other country, or if you chose specific samples and then you want to compare one sample against the other. Those two samples may be two samples of people who are under different risk, like smokers versus non-smokers, but they can also be some people who are getting different treatment, like they all can have some form of cancer, and then one of them are getting one kind of treatment, other, and you're comparing the treatment. So there are all sorts of reasons why you want to be comparing this occurrence. And for this simple method of 4 steps, we have derived most of the knowledge in medicine to this day, because most of biomedical research to this day has this kind of stepwise approach in its root, okay? That you firstly define what the disease is, and then you count the frequency of the disease in some populations, and then you cross-tabulate against possible risk factors or possible interventions, and then you compare the effects of risks or the effects of interventions in various populations, all right? So that's how we derive knowledge. This is how we advanced medicine from very early stages. And we can use some study designs once we agree that we will use these methods. There are several study designs, and one is the cohort study. That's every epidemiologist's favorite design, because it is just so good in so many ways, protects us from so many possible mistakes. And don't get confused if you see the prospective or longitudinal. This is all exactly the same thing. Cohort or prospective of longitudinal is talking about the same design, the design that starts now and then goes into the future. Then you can have a subset of a cohort study, which is a controlled trial, which can be a randomized controlled trial, double-blind controlled trial. Don't be thinking, what is this now? A controlled trial is really a subset, a very specific subset of a cohort study, which is making cohort study even better than it is. Then you have a case control study, and I will show you. This is usually something that we use for exploratory purposes initially. Why? Because it's cheap and it's quick, all right? So it's much cheaper and much quicker than conducting a cohort study. Cohort study in terms of design is a better design, gives us better answers, protects us from mistakes. Case control study is prone to many possible mistakes. It's not an ideal design by any means, but it is just so much more quick to get some answers that is very important to us, and it's so much cheaper as well. And then you have cross-sectional study. Cross-sectional study is the poorest possible design if you want to infer relationship between some risk factor and burden of disease, because the confounding effects and biases are enormous. So I would never try to infer any relationship between risk and disease or effect of intervention from a cross-sectional study. But it's still useful because it's useful to measure the burden, to establish prevalence. And sometimes when you're measuring the burden and taking the information on risk factor exposure at the same time, you can start thinking about some possible associations. Although, as I said, I wouldn't try to convince anyone based on a cross-sectional study that there is any association between a risk factor and any disease. So remember this is the weakest of all designs, cross-sectional study. And then case control study is a bit better, and then cohort study is much better, and then randomized controlled trial, especially if it's double-blind, that's the best design we have in epidemiology. And I'll explain why is this, all right? So cohort or prospective or longitudinal, all the same thing. A cohort study starts in present and goes and extends into the future. So starts in present, goes into the future. What does it look like? You really want to establish whether some risk factors have effects on some diseases. So this is why we usually use it. We want to establish that smoking is really causing myocardial infarction here. So how are we going to do it? We take 1,000 people who smoke, we take 1,000 people who do not smoke. We take them all in present, and then we follow them for a very long time. And after a very long time, 600 of smokers will get heart attacks, but this could be in 30 years' time. And then at the same time, in the same amount of time, only 200 will get, non-smokers will get the same health problem, okay? And then what can you do here? You can calculate several risks. One of them is so-called absolute risk, okay? Absolute risk is the same as incidence pretty much. You will see that later. So absolute risk here is 60%. Why? Absolute risk is just the risk that over a period of time something bad would happen. So you have to define what period of time are you going to take. This could have been 30 years here. And then this just means absolute risk after 30 years that the smoker will have a heart attack is 60%. And for a non-smoker is 20%, okay? So that's absolute risk. But when you know these absolute risks, you can calculate something that's very interesting to any epidemiologist, which is a relative risk, okay? And you get it by dividing absolute risk in exposed with the absolute risk in non-exposed. You divide those two and you get number 3, which means that the exposed to risk factor have 3 times greater chance to develop a problem over the same period of time than those who are not exposed, okay? So that's really useful to know because, you know, if someone's smoking, someone's not smoking, I can tell the smoker, you're 3 times more likely than this person to develop heart attack. That doesn't mean that you're going to develop it because you can see that some people didn't. And this doesn't mean that the non-smoker will not develop it because you can see that some people did. But at least you can tell them, well, you know, you're not operating at the same level of risk. You're taking 3 times greater risk than the other person if you're smoking. Okay? So relative risk is always the most interesting in health research because we need to try to prove that it's greater than 1. If the relative risk is 1, that means that you're dividing the same number with the same number. That means that both absolute risks are the same. And then you divide them, you get the relative risk, which is 1. You need to prove, as a result of your research, that relative risk is significantly different from 1, and then you have proven that something is a risk factor, and this risk factor contributes to the burden. Now, what is a randomized control trial? That's even better because sometimes you do a prospective study, but there is something else about these people who are exposed. So all smokers could also be coffee drinkers and non-smokers may not be drinking coffee. So you think you're exploring the effect of smoking, but in fact you're exploring the effect and capturing, and this is all due to the effect of the coffee drinking. So, you know, to protect yourself from that kind of a problem, you start with smokers who you believe are maybe then all going to be coffee drinkers, and you have to randomize them just completely randomly and let one group randomly quit smoking and one group continue smoking. But they have to be random so that all things that smokers also have in common, like coffee drinking, are randomized. So that you expect that all of them, this group of 2,000 people, will have the same distribution of all other risk factors apart from one thing, which is that one group continued smoking and one group quit smoking. And then if you see this kind of difference, then you can be sure that this is due to smoking. I mean, you can still not be completely sure, but if the sample size is big and the randomization is truly properly random, then there's no reason to expect that all the other risk effects would not be completely randomly distributed between those two groups and that they should then be the same. This is why we're doing this randomization, to completely level all the other background effects and try to get rid of this confounding. Confounding is the biggest problem. We can get rid of the biases by planning study designs carefully. We can get rid of the chance effects by expanding the sample size to very large numbers, and then all the chance effects just disappear. But confounding is always something because we can't measure and think of any factors that could be correlated. So confounding is so difficult to get rid of, and this is why we need to randomize And so the question, if the question is, why do we randomize? We randomize to make sure that all the possible confounding effects are the same between those two groups which we are randomizing, okay? And then, again, you have the relative risk, but this time you're far more sure that this relative risk really is a consequence of smoking, because in the previous slide, this relative risk could have been a consequence of smoking, but it could also be the consequence of anything else that smokers do or have which non-smokers don't. Maybe they're of lower socioeconomic status, maybe they're of lower education, maybe they're of lower socioeconomic status, all right? So those things could have contributed, right? But here, when you randomize a group of smokers, then it's really down to smoking if you see such a striking effect, all right? Now, let's move to case control studies. What are the case control studies? They are also called retrospective studies. Why? Because you start now, but you look back. So at present, you take some people and then you look in the past. Here, we don't take people who are exposed and people who are not exposed. We take people who already got the disease, and then we take people who did not develop a disease yet. And then we ask them about their history of exposure. So this is a completely the other way around. There we had everyone exposed and no one exposed. Here we have everyone diseased and no one diseased. And we are trying to look, what was the exposure to risk? Was it bigger among those who got the disease or not? These studies are easy to conduct because we can conduct them in a hospital setting. We can just go to a ward and take all 100 people there who have heart attacks, and then we can take somewhere else from the hospital 100 people who came because of the knee injury, for example, which we presume is random, although that's a very big assumption. And this is what the problem is with the case control studies, that your sample, your control sample is never a proper control sample. You never know whether you are really comparing like when you're comparing people with a disease and people who are not having a disease. And hospital-based controls can be very, very difficult to serve as a good control group, because they're in hospital for some reason, so something must be wrong, and it's very difficult to pick a control sample from a hospital which is not in itself somehow biased and could be under systematically greater exposure to some of the risk factors that you're exploring. And note that in the case control design, you cannot establish absolute risk, because absolute risk is a risk of something bad happening over a period of time. And here you don't have a period of time. You have to go back. So it's not about something bad happening. It's about being exposed some time ago or not. But it's not about something bad happening. Something bad already happened to all these people, and it didn't happen to these people. So you can't establish absolute risk. If you can't establish absolute risk, you cannot establish a relative risk either, because you get it by dividing the two. So what can you do? You can only estimate relative risk by a measure which is called odds ratio. And you're going to see a lot in the literature this odds ratio. Odds ratio is an estimate of the relative risk. It's the odds that the case was exposed divided by the odds that healthy control was exposed. And this is how you measure it. If this is A, this is C, this is B, and this is D, then you do this and you get a number 3.5, which is very close to number 3, which we had before as a relative risk, okay? So it's not the same, but it's a good estimation of relative risk. It's the best we can do under the circumstances. But please don't make a mistake if someone asks you what is the relative risk in a case control study, or if the question is a case control study established a relative risk of 2.5, then you need to immediately know that this is not possible, because the case control study or retrospective study cannot establish a relative risk ever. They can only assess it through odds ratio, all right? And then you have a cross-sectional study or a prevalence study, where you just go to some big population, which is this big square, and define who had a history of myocardial infarction. And you see that 5% of people in a population will say that they had myocardial infarction, all right? And then you can also at the same time ask them, were you a smoker before that? And you can ask the rest of the population, are you smoking? And then you can try to infer something from here, but this is just so dangerous because firstly, some of the people who got myocardial infarction have died and they're no longer in the population. Some people who got myocardial infarction as a consequence quit smoking, so this is called reverse causality, when you're finding a less prevalence of smokers among myocardial infarction prevalence studies because they were all told to quit smoking. So there will be fewer smokers perhaps here than here. So firstly, you lost some people because they died, and secondly, you may have a reverse causality operating, that people change the behavior and now it looks like there are fewer smokers among those people than in the general population who did not yet get the myocardial infarction. So this is why we don't try to make any inference from cross-sectional or prevalence studies, and it's always all happening in the present, okay? So those are the three types of studies. And then a little bit about this statistics, which is so scary to everyone who goes into health research. They're like, oh, we would love to do some research, but we can't see these numbers, these formulas, we don't know these statistics, we don't even want to know anything about it. This is so scary, this is so, you know, we don't know how to. Okay, so look, this is just so silly to be worried about this, because 99% of research is really designing, planning, conducting research, gathering evidence, and then showing something like this, you know, having like this. And when you see that there is 600 here and 200 here, why do you need the statistics? I mean, for goodness sake, you can see that this is 3 times bigger than this. Why do you now need to say this is p-value less than 0.000 whatever? You know, who cares? I mean, my answer is that these guys are 3 times more at risk than the other guys. Who cares what the p-value is? And so if I do it 10 times over, every time I'm going to get the different p-value. What's important is that I have designed my studies well, I have confidence in my data, I know what I was doing, I was thinking about the bias, the chance and confounding in my design, I made sure to minimize their effects, and now I have this answer, and to me, I'm very happy with this answer. It's a very clear answer, it's telling me something, and why do I need to care about what is the p-value of this, all right? So, but sometimes situations are not clear. So let's just, you know, touch upon the statistics, because this is something that once you have conducted 99% of your research, you can just pay a statistician to come and to just, you know, calculate based on your data your p-value, and then you can put it in your research and you can write the paper. So really, you do not need to be scared of this. The health research and the global health research is about designing the study, conducting it well, understanding your research question, understanding your answer. It's not about this little number that has to be put there in the paper, okay? And what do we mean by statistics? Statistics is a tabulated numerical information, and it's a discipline which is the art and the science of handling uncertainty. So statistics is really about handling uncertainty. It is when you get your answer, but look, now I want to say something good about statistics, because so far I was downplaying its importance to make you less scared of it. But now I want to explain why is it also extremely useful. It's extremely useful because when you get your answer, you want to know what are the chances that this answer may be wrong, all right? Because it's great to see that something is 3 times bigger than something else and you have a clear answer. But still, in the back of your mind, you're thinking, what is the chance that I may be wrong here, that I'm misleading the policymakers, that this is really not the case? And then it's much nicer if you can come in front of a policymaker and say like, look, there's only 1 in 10,000 chance that I'm wrong, than if you can say, well, there is 1 in 3 chance that I'm wrong. That's obviously a very big difference, because it's nice if I'm a policymaker that the research comes to me and tells me, well, look, you know, smokers are at 3 times greater risk, we need to abolish smoking. But I'm a policymaker, I'm like, man, abolish smoking, people love to smoke, you know, people enjoy smoking, it's very difficult to quit. If I am going to put my politician's career on the line, you know, I need to be absolutely certain this is true. So how certain you are that this is true? And if you say, well, 1 in 3, you know, I'm 67% certain, he's going to like, man, that's not enough. But if it's like 1 in 10,000, then it's good. And you know where this is relevant? Well, climate change, all right? So look what's happening. The climate change scientists are in a horrible situation. I wouldn't like to be in their skin because, you know, they're seeing the climate's changing, and there are two research questions. Is the climate changing or not? Well, it looks like it's changing, but they're only 93% sure. And the implications are that we need to, you know, slow down the economy, abolish, you know, drilling oil, and saying people not to use cars anymore, and save energy. I mean, these are enormous consequences if this is true, but they're only 93% sure. In science, usually you need to be 95 or 99% sure before you're able to go out with your results. And then there is even bigger research question, which is this climate, if it's changing, if we were 95 or 90, even if we're 99.9% sure that the climate is changing, is this really due to human effect, or is it just sun having its cycles, or something else that we can't even understand, magnetic fields, or just a normal thing that happens from time to time with Earth? You know, so is it human induced? And that is where the uncertainty is much bigger. They're not certain at all. They may be certain 70, 80, 90%, but certainly not 99%. And then the big industries are going to say, look, if you're not 99% certain, we're not going to change anything. So, you know, they had huge fights over what to do. Those who were really like scientists, they said, like, we don't want to embarrass ourselves and say that there is some climate change and global warming, and only to be wrong, and 10 years later we are completely ridiculed. You know, the scientist doesn't do that. But then there was another group of scientists who were saying, like, look, if we are right and we don't speak up, we're all going to be doomed if we don't do something. So let's forget about statistics here and level of uncertainty, and let's just go and tell people that we're all in big trouble. So you see how it's all working. So statistics is extremely useful in telling you how uncertain you are about your answer. And it's really how we do science, because we don't do science by proving that something is right. That's not how we do science. So it's not, people always have hypotheses and research ideas and research questions, but we don't ever prove anything right, because we can't ever prove anything to be 100% right. What we can prove is that the alternative is extremely unlikely. So, you know, that, and at some point it just becomes so unlikely that we have to completely abolish it, forget about it, and accept this, what we hypothesized as the new truth. So if you think that you understand some new truth, the way to convince everyone else in the research community that they should accept your view is by conducting an experiment or a research where you're going to show that the alternative, which is at the commonly held belief, is just so unlikely in view of evidence of the data that you have to reject it. So we are proceeding from you know, known to unknown. We are on these boundaries by rejecting the null hypothesis that there is no difference, but we can only reject. We always start with the null hypothesis, which is, this is what we know. We want to keep this sacred. We don't want to drop. We don't want to change anything, any beliefs, unless we're absolutely certain, right? So you're protecting yourself. So this is why these p-values have to be so small, because in science it is far more dangerous to take the wrong path than to just wait for a little while and believe in something wrong until you're absolutely certain. So you don't want the resources and the time of the people to be wasted by chasing stuff that's not true. So for things to be accepted in science, you have to really be certain that you can reject all the previously held beliefs. So null hypothesis is always what you start with and assume it to be true, and only when you can use the information and data from your research to show statistically that the null hypothesis becomes so much less likely than you thought, that it really reaches ridiculously low level of likelihood of 1% to be true, for example, then you can reject it and say it's 99% likely that it's not true. So this is how we go in science, not by proving that we are right, but by showing that the alternative view is just so unlikely that we should all discard it and accept the new view as a knowledge. And this is why knowledge is fluid, because knowledge is really, what is human knowledge? Human knowledge is just the sum of all our hypotheses and all the probabilities that we assign to those hypotheses based on the best possible information that we have gathered so far. So, you know, you gather information, and we're constantly gathering more and more information, and you adjust the probability that you assign to various beliefs. So, you know, and this is why human knowledge is not something that's kept in books, because if you look at the books from 50 years ago or 100 or 500, you would see all sorts of things there that we no longer believe to be true. Why? Because we were gathering evidence all the time and information, and in light of this information we were changing the probabilities that we assigned to various beliefs, and some of these things just had to be discarded over time, all right? So the classical science is hypothesis-driven science, and the hypothesis is incorrect until proven correct beyond reasonable doubt. So similarly to how we imprison people, you assume that the person is innocent until you can really prove beyond reasonable doubt that it's guilty. In the same way we advance science, we assume that the new hypothesis is wrong until you can prove beyond reasonable doubt that it's probably should be considered to be right. This is why we have such stringent p-values and large samples, because it's so much more dangerous to take science down the incorrect path and waste resources than to reject the correct path until there is more conclusive evidence. In the same way, it's more dangerous to imprison an innocent people than to let a guilty person walk free, because the guilty person will likely commit some problem again, and things will clarify over time whether he is guilty or not. The same thing with science, you know. So, but now we have modern science. Modern science, in 21st century, we entered a completely new era of science and of research, where we are doing hypothesis-free science. We no longer need hypotheses. This is strange, because you see, the knowledge, the human knowledge, was advancing in little steps by, testing. First you needed to gather some knowledge. Based on this knowledge, you were thinking a lot, and then you came to some ideas, you connected some things, then you proposed the hypothesis, then you were testing the hypothesis, and in small steps we were moving from knowledge to expanded knowledge. So only a few people who were literate and who were educated could really be scientists, all right? And this is how it all progressed. But now we came in an era of science where we no longer need to do science like that, because we can measure stuff so precisely now that we can just measure everything and then put it in the computers. So one big thing that's changed is our ability to measure things. Before, it was not very good to measure anything. Now we have these big machines that can measure all the sorts of stuff from your blood, thousands of things with perfect precision. It's replicable, it's always the same result, no matter what. And similarly, we can take the DNA and we can scan the genome. And this is a result of the genome-wide scan. You see, each color is one chromosome. We have 23 pairs, so there is a 23 chromosome in a haploid genome. And each dot is one place in the genome. So look at this now. This is how we do hypothesis-free science. We measure something like uric acid in this case. We measure uric acid in the blood, and we want to know which gene controls uric acid. So if we did it classical way, we would need to firstly study all 25,000 human genes and what do we think they could be doing, and then we should hypothesize which 10 or 15 genes may have something to do. Then we would develop a design that would look at the genes, people who have this variant of those genes and that variant of the genes, and whether there is a difference in their uric acid level. That would be the hypothesis-driven research. Now, we don't have to know anything about any gene. Look, we just screen the genome, read it, okay, and it's 3 billion letters, okay, many, many dots here. And each letter could potentially be associated with uric acid. So we don't need to know anything, we just need to measure it perfectly, precisely, and we measure perfectly the uric acid. We do this in 100,000 people or even 500,000 people in the UK Biobank. So we make massive sample sizes, all right? We need those big sample sizes because we're doing so many multiple testing that by pure chance, testing so many letters in the genome, you are going to get some false positives. So this is the problem with with this hypothesis-free science. But remember, no hypothesis, just massive measurements, okay? And look, we don't want to have 3 billion letters because the likelihood of false positives would be so high that it would be difficult to manage. So here we actually have 300,000 of these dots. So we reduce this 3 billion to 300,000 of very most informative polymorphisms. And now we're looking what is the p-value of each one of them to split people in this sample to those with high or low uric acid. And this is the p level of 1 in 1,000. This is a p level of 1 in 1, 2, 3, 4, 5. So this is probably 1 in 100,000. Now look at the beauty of this. So the chance here is 1 in 100,000 that you're wrong. So for this dot to reach as high as this, that means that the chance that it doesn't have anything to do with uric acid levels is less than 1 in 100,000. But look, this is not enough certainty. Why? Because we have 300,000 markers. So you expect among 300,000 markers that 3 of them will show this p-value just by pure chance, by the chance of distributions of people within these samples by uric acid if you did this 300,000 times. And look at this dot, look at this dot, and look at this dot. Those are the 3 dots which are false positives. Although the p-value is less than 1 in 100,000, they are all false positives. None of these things here have anything to do with uric acid. What does is this on the chromosome 4, this locus, 1, 2, 3, 4, 5, 6, 7 markers go all the way to less than 10 million or 100 million. So the chance that this place here in chromosome 4, which is the gene SLC2A9, doesn't have anything to do with the uric acid levels is less than 1 in 10 million. So that is the level of certainty you need and that you can be happy with to decide that this has something to do. But you're absolutely certain. We reached the level of p-values of 10 to the minus 200. So it's more certain that something in the body is linked with some disease or some trait than that the universe actually exists, you know. So we can be absolutely certain of those things thanks to this hypothesis-free science. And we don't need to know anything about it. And then the computers are now so great. So I said, what is enabling hypothesis-free science? Firstly, massively precise measurements, okay? And secondly, computing power, the computers, because we need to store these massive amounts of information and we need computing power to then calculate all this in hundreds of thousands of people with hundreds of thousands of markers. So you need enormous powers. For weeks, computers need to work. And then computers are brilliant because you then, you can take this peak that you found and then expands to this chromosome and then expands to the region and you can see which gene, what markers, and you can start working from there and trying to figure out why is this correlated with uric acid. So why is SLC2A9 gene correlated with uric acid? You start studying the protein which it develops. So what is so appealing about this hypothesis-free approach to science? It's virtually completely free of any human bias or opinion because, hypotheses were all based on knowledge that we couldn't be certain of. You needed to acquire the knowledge and then you needed to be clever, think of a hypothesis. But then many people, unfortunately, were so convinced of their hypothesis that they would kind of, try to make results look a bit better. When there's something wasn't fitting, they would kind of like drop it and so to make it look better. But computers don't do that. They just tell you exactly how things are. There is no room for opinion, bias, any kind of cheating in science. It doesn't depend on any previous human knowledge. So we can make large leaps forward in knowledge and discovery. We can find things that we maybe wouldn't find for another 500 years because the science wouldn't get there. But now we just measure everything and look, and suddenly we find the things that are absolutely certain to be true. So basically we are getting the correct answers before we ever asked the question. Before it was you ask the question and you try to answer the question, yes or no, test the hypothesis. Now we get the correct answer. We get these two things are certainly correlated. But why? So we have to play detectives and work backwards. Science now is working backwards from a certain knowledge to why is this so, rather than gathering knowledge in a linear forward way. And it's all based on extremely accurate measurements. So the developments of high precision measurements possibility to store the biobanks, develop large biobanks and computing power have enabled us hypothesis-free biomedical research and health research. And this is now becoming really exciting and real mainstream. And we're learning far, far more than we could have imagined 20 years ago, thanks to all these developments. It's a completely new era of science, all right? Okay, thanks very much. So that was the first in the series of lectures.